In this lesson, we're going to work with a different form of a line called point-slope form. So far we've seen the slope-intercept form and the standard form we've seen, but we're going to work a little more with it in the next section. Looking at this graph, I'm going to show you where the point-slope form really comes from. If you look at the graph and there's a general point, which we're going to call xy, and then a specific point, 2, 5. Again, xy is going to stand for any point on the line. But if we set up the slope formula as y minus y over x minus x, like we've worked with before, I'm going to use the general point xy for my first y value. So y minus 5 over, and I'm going to start with the general x value, x minus 2, we know that that's equivalent to the slope of that line. So I can put m, but in this case we can actually count the blocks and see that if we go up 2 and right 3, we're definitely going to have 2 points on the line that are integral values. So we can say that the slope of that line is 2/3. Now, if I just multiply both sides of this equation by x minus 2, just taking that x minus 2 out of the denominator, we'll get y minus 5 on the left, and then 2/3 times the quantity x minus 2. Right? So we just took the original equation and I'm multiplying by x minus 2 on both sides. And that actually is point-slope form. So in general, the point-slope form of the equation of a non-vertical line that passes through a given point x1, y1, so there's a specific point, with a slope of m is y minus the particular y value, y1, equal m times x minus x1. So here I've given you in black there the point-slope form. So we're going to do our first problem. Suppose that 5, 2 is a point on a line with slope of 3/4. Write the equation, the line, in point-slope form. So literally in this form, if you're given a point and a slope, you really don't have to do any work. You're ready to write the equation of the line. So again, the form, the y is in general, which stands for any y value on the line. And then we subtract a particular y value. So in this case, we have the 0.52. So we're going to subtract 2 because that's the y value of our point. And then equals, the slope is given, so that's 3/4. And then in the parentheses, we have our general x value, which stands for any point on the line, minus the particular x value of the point we have, which happens to be 5. So notice I didn't have to solve for anything. That is the point-slope form of a line that passes through 5, 2 with a slope of 3/4. So if you start with the point-slope format, which is there in black, then you really just fill in the particular point you have, and you leave the x and y as variables, and you fill in the slope as a number. So this equation, now that you see that x, y stand for every single point on this particular line. So let's try another one. Suppose that the point 3, -4 is a point on a line with slope 2/5. Write the equation of this line in point-slope form. Okay, so think about what you're going to do with the 3, -4. Okay, so we're going to write y minus, and now y1 is -4. I'm just going to write it for now. And then the slope, so are you thinking that's where you put the 2/5? And then x minus, and you look up for x1, which happens to be 3. So now this time notice how we have the y minus a -4. And typically, of course, how you write y minus -4 would be y plus 4. So sometimes you don't see the minus that's in the formula because you were minusing a negative number, as we did in this case. But this is the point-slope form of a line that contains the point 3, -4 that we were given, and has a slope of 2/5. Again, notice we didn't have to do any work. We just substituted the point and the slope. Try another one. Make sure you're putting these in your notebook. So you should have gotten y minus 8 is equal to 1/2 times x minus a negative 7, so that would be rewritten as y minus 8 is equal to 1/2 times x plus 7. And that's point slope form of the line that contains negative 7, 8 with a slope of 1/2. So now we're going to start with an equation that is in point slope form and see what we can determine from it. Remember that when we had equations in slope intercept form, like y is equal to negative 2x plus 5, we were able to look at that knowing that's in slope intercept function form, and we were able to just say, well, we know the slope is negative 2 and we know the y-intercept is 5, because that's what the form tells us. It's the same thing with point slope form. When we recognize that it's in this form, y minus y1 equals m times x minus x1, then we're able to simply pick out the x and y value of the particular point. Now, notice that the x plus 3 doesn't match up correctly. So again, I'm going to rewrite this as y minus 6 equals 7 times x minus a negative 3. Now it matches with the formula. So the minus is where it should be, right there. So the x1 value then is negative 3, right here. So we know a point on this line is negative 3. We come over here to read the y1, and the minus matches up fine, so we know the y1 value is 6. So our point is negative 3, 6, and then the slope, of course, is the coefficient of that quantity with x in it. So the slope is equal to 7. So from the point slope form, just like the word implies, we can pick out a point and a slope. So here's another equation in point slope form. Again, the minus here doesn't match up, so if we rethink that as y minus a negative 1, and the right side matches up fine, so we should be able to pick out the point 9, negative 1, and a slope of negative 2/3. So try this one. So did you get a point of negative 3, 4? Again, remember x minus negative 3, the minus is in the form, and a slope of negative 2? Good. So now we're going to look at a word problem that lends itself pretty easily to the point slope form. If you remember earlier in the chapter when we looked at the slope intercept form, we had some logical equations that came from an initial value and then a constant rate of change that were easily written in slope intercept form. But if you look at this one, how temperature affects running speed, the best temperature for running is below 60 degrees Fahrenheit. If a person ran optimally at 17.6 feet per second, he or she would slow by about 0.3 foot per second for every 5 degrees increase in temperature above 60 degrees Fahrenheit. So in this case, we'll look at one specific value as a pace of 17.6 at a 60 degree Fahrenheit temperature. But what we want, let's try to figure out what the slope is. So slope is going to be that change in pace over the change in temperature. So in this case, that change in pace is we have a slowdown of 0.3 foot per second, so and treat that as a negative 0.3 for every increase in 5 degrees. So there's the change in temperature. Remember that triangle, that's a delta Greek letter that means change in pace over change in temperature. and we get about negative 0.06 for our slope. So now we want to use that 1 point that they gave us. So for a temperature of 60 degrees, we're going to use that optimal pace of 17.6 feet per second. So we're going to use that as our first point. So again, we have the point right there, 60, 17.6. We figured out the slope was negative 0.06. So now using the point slope form, we just substitute that 1 point, 60, 17.6, and substitute our slope. We have an equation of the line, again, in point slope form. Now, as we said, a lot of formulas are written in function form, that slope-intercept form. So if we simply distribute the negative 0.06, we're going to get that line there. Right, make sure you distribute. And then add 17.6 to both sides, and that's going to give us this formula for the optimal running pace based on the temperature. So using that formula, we could plug in any temperature and figure out what the best pace would be. And we'll do that next. So if we want to determine what the optimal running pace would be for a temperature of 80 degrees Fahrenheit, we'll just use our formula, negative 0.06 times 80 plus 21.2, and just multiply. And again, positive times a negative, so we'll get our negative 4.8, so the pace would be equal to 16.4. That's feet per second. Okay, so here we see that again worked out, and you can see the graph at the left that represents that optimal running pace at 60 degrees and the 80 and 16.4 that we plugged in, and you can see that it fits the graph. So next we're going to work on standard form. So replay any of this that you need to.